So when we talked about facets and views, we talked about the fact that data is often large and complex and too big for us to see in one space. And so we talked about ways that we could select different parts of the data to view, break it down into facets, connect those views together in order to get a good picture of the data. Sometimes we just need to reduce the amount of data that we're working with, though. It can be that it's just too big to be visualized altogether. In terms of computing power, there's just too much of it. It could be that there's just no way to really get insight if it's all there, and so you need to select or smush it down in some way. So that's what we're going to talk about today, different techniques for data reduction. We're going to start off by just talking about why do we need to reduce the data or abstract it into something else, and then we'll talk about a few different techniques: segmentation, sampling, clustering, aggregation, and dimensionality reduction. So here's the core of the issue. We're creating tons of data now. Every 2 days, we create as much information as we did from the very beginning of time until 2003. 90% of all the data in the world was created in the past 2 years. And of course, that rate is just picking up. So we're creating data and recording data in a way that there's just so much of it that it's impossible to look at it all at once. And so the question is, how do we deal with this growth and analyzing all this data? So by 2020, we expect that the amount of digital information will have gone from 3.2 zettabytes today to 40 zettabytes, so over an order of magnitude increase. This is huge, and we need to be able to deal with it and understand it if there's any benefit to having all this data. To understand big data, we also need to know what our limits are. The technical limit that we can deal with is about a billion items, 1,000 million items. That's technically, but humans can only deal with about 100,000 items. Once you get beyond that, we can't really deal with it. We start doing abstractions automatically in our head, or we get confused. And so for visualization, the point is to help humans gain insight from data. And so we have to take these billions of pieces of data and put them into a format where you're not pushing past that human limit of about 100,000. That means you somehow need to shrink your data down, whether it's aggregating it together, clustering it together, or just sampling some of it out. So you're dealing with numbers that are within that human limit. So why do we reduce? Why do we abstract? Segmentation allows us to split the data set into pieces that we can then look at, and that gets us within that human limit. Sampling is also reducing the data, where we're randomly choosing data points to show, and that hopefully gives us a representative view of the data without having to look at everything. Clustering allows us to find patterns. It reduces what we have to look at and sometimes aggregates things together. Aggregation is combining points. And so you could imagine, say, looking at your personal social network, and instead of looking at each person, you look at the main social groups that you have and see how they interact. And dimensionality reduction is exactly what it says, reducing the dimension. So instead of looking at all the different attributes of the data, we're going to somehow reduce that down so we're only looking at part of them. So let's talk about each of these techniques. First, we have data reduction through segmentation. So segmentation is reducing the complexity of data by splitting it into parts or segments. We perform analysis and transformation independently on each segment. So I'm going to break my data down into chunks, and then I'm going to analyze each chunk separately. Once I've done that, I'm going to combine the results into a coherent whole. Basically, what I'm doing here is breaking the data into problems that can be solved in parallel. One classic space that we see this in visualization, not information visualization, but more broadly in visualization, is in computer graphics. Computer graphics can be called embarrassingly parallel. There's very little effort required to separate this into subtasks. So there's actually a ton of computer science that goes into animation at Pixar for movies like Toy Story. There's a lot of really complex work that needs to be done to render different textures, different parts of this. But fortunately, it's easy to break that into parts. You can have one process going that's going to render the background. There's some that's going to render the floor. There's some that will render the texture of the clothing. There's some that will render the facial expressions. And so you can have different processors rendering each of those pieces separately and then putting them all back together to give you one coherent view of the image. Essentially what we've done is segment the problem by segmenting the data into the different pieces, background, floor, clothing textures, face, and so on. We work on each of those problems and then we reassemble them at the end. Another way to reduce the data that you're working with is sampling, where you take parts of the data and use that instead of using everything. The fact is that sometimes it's not necessary to process the entire data set. If we have 1 billion observations and we process all of them, it doesn't necessarily give us better results than if we were to just take 1 million of those at random and select that, because that million sample probably will average out to be about what we would get if we had all the data points. So it can be better to try not to summarize all the data, because summarizing all of it can be really slow. It can be confusing if we try to visualize it, but we can get pretty accurate results if we just take a random subset and deal with that in our analysis. So sampling, you're going to take a random subset. Ideally, that averages out to what you would see in the entire data set. And there are ways to sort of guarantee this. So there are things called Monte Carlo algorithms. These are kind of like coin flipping algorithms to randomly select part of your data. They're good because we know how long it takes to run them to pull out the sample, so it won't just be going forever. And the results tend to have a pretty small difference from what you would see on the whole data set. So there can be a little bit of error in there, which means that your averages, say, are going to be a little bit off from what you would have if you had the entire data set. But usually those errors are so small as to be something that you can ignore. Especially when you're doing visualization where you're trying to get more general insights. Sampling often is really effective. Now, depending on what kind of data you're looking at, your sampling techniques may vary. There's a lot of research on what's the right way to sample depending on what data you're looking at. But it's a good technique that allows you to just work with a subset, really reduce the volume of data that you have, but still get good insights. Clustering is another technique for doing data reduction. With clustering, we're going to organize data into patterns based on some kind of similarity. And there's a few ways to do clustering analysis. These are not specific to visualization, but in general when you're trying to reduce your data. There's unsupervised clustering, where essentially you have an algorithm that's going to look at the data and just try to detect, based on its structure, what are some similarities and what data points should be clustered together. This is typically a form of machine learning, which is a kind of artificial intelligence. You can also do supervised classification, where you give a set of rules for how things should be clustered together. The components of clustering are that you have elements. These are basically your entities. They would be rows in tabular data. They're your n-dimensional points, where each dimension is an attribute. So you have each item in your data set, which are your elements, and then you have some similarity function that's going to try to figure out which data points are similar. We've actually seen cluster analysis at play already when we were looking at social networks. I showed you how to use the modularity class algorithm in Gephi, which would take your visualization and it would cluster nodes together into the same classes based on essentially how close they were in the graph. It did that by looking at distance in the network, so looking at the paths and the edges that connected nodes or that connected them across a series of links. And what we got were nodes that seemed to be in the same groups clustered together. That works pretty well if you have a good structure. Now, not all data is network data, so you've seen this work on networks, but you can also use this when you're looking at tabular data, multidimensional data where you have lots of attributes for each element. An example to show that at work is this tool called Clustergrammer. I have a link here so you can try it out. But if we flip over to that, so what we're looking at here is an interactive demo. Across the top on the x-axis we have different cell lines, and if we mouse over them we get basically a little tooltip. On the y-axis we have different genes, and so we're looking at cell lines and genes. We then have one column here that tells us the gene type, and that's basically interesting or not interesting. For the cell line, we also have a couple rows up here. One is going to tell us the category, and the other one tells us the gender of the cell line. Is it male or female? And then in here, we actually have our cells that are giving us the values for a particular cell line in a particular gene. Now, most of us don't have, again, this genetic background to understand what all of this means, but you get the idea that there's a lot of data here, and we can look at it in a variety of ways. So this tool, Clustergrammer, allows you to interactively take different views on this data. Right now, the cell lines and the genes are sorted alphabetically, but we can sort them in a variety of ways, and one option is to sort by cluster. So if we change the row order to go by cluster, and then change the column order, watch how things change up here. So if we change that, we can see that we have different groupings now. So all of these genes in category 1 happen to get grouped together because they were in a cluster. We also can see that there's a little bit of grouping that happens down here based on gender. And you can see that there are some interesting patterns. We have a few groups of category 5 genes up here. And there also seems to be a bit more structure in the data that we're looking at here with that clustering. So we can see that there's some more clumps of red in a few places, and then some bluer segments as well. Now, you need to understand the data to really get insights here, but the idea is that when we just kind of have our data ranked in ways that maybe don't have that clustered meaning, you can certainly get insights from it, but the clustering itself allows other patterns to emerge. There's different ways to do cluster analysis. Some is hierarchical, so you're building clusters from existing clusters. You kind of start off with a big idea of what your cluster is going to be. That becomes your top-down approach, and then you can break that down into subclusters. You also can go bottom-up, so start by trying to find little clusters and then connecting them to other little clusters to make higher-level ones. So you get a hierarchical view of the data. There's partitional cluster analysis, where you're basically trying to find points in the data that separate one group from another. So one way that would be very straightforward to do this, if you have multidimensional data about people, maybe you have gender. And so gender is a way that the data easily gets separated into a couple groups, or depending on what your options are, maybe you have male, female, and other as an option into 3 different groups. That's going to be one way that you separate your data, and then from there you could break it down and partition it according to all sorts of other values. Lots of data will have these natural partitions where there are some points that tend to be on one side of a threshold and other that tend to be on the other side of the threshold. And that becomes a way that you can separate them into clusters and then further break each of those clusters down. There's also density-based cluster analysis, where you're creating kind of arbitrary clusters. They're not based on any rules or elements, attributes of the data, but it depends on the density of the points. This is sort of what we saw in the cluster analysis that we did in networks. You can visually look at them, and the clusters tend to have a lot of node density within them. And that can also happen with multidimensional data, like tabular data. There can be density of points that all kind of have values for an attribute around a specific value, and that can become its own cluster. Another way of doing data reduction is aggregation, and this is actually tied quite often to clustering, where, again, imagine a network example. You have a whole bunch of nodes, maybe too many to look at. You can run a cluster analysis on that, and then instead of just highlighting all of those nodes based on what cluster they're in, you actually can aggregate them together. So make one kind of mega node that represents an entire cluster and all the nodes within it. And instead of looking at how each individual node connects to each other, you can aggregate the edges between the nodes in each cluster to show connections to other meganodes representing other clusters. You can also aggregate data in other ways. So you can group things together based on features. So say you could group nodes based on gender and then average all of the attributes within that group. You can also aggregate by bringing points together. For example, if you have financial data that's done quarterly, you may want to aggregate into years. And then you wouldn't be taking the average, but you'd actually be summing up the data from sets of quarters into years in order to reduce your data from a bunch of quarters into a bunch of years and adding up all of the information to get the proper value. Dimensionality reduction is another way of reducing your data, and this is a little bit different than the others. Instead of reducing the number of data points, the number of items that we're looking at with dimensionality reduction, instead we're removing features. So data abstraction deals with reducing the number of cases. That's what we've been talking about so far in all of our examples. But dimensionality reduction reduces the number of variables, that's dimensions, that's attributes essentially that we're doing. So there's two main approaches to this. One is feature selection, where you're selecting a subset of the original variables or attributes that capture all the information. So sometimes you may have attributes that basically reflect the values of other attributes. And so then you can just select the ones that kind of have all the meaning that you need. You can also do feature extraction, projecting your original space into a lower dimensional one. These tend to get pretty mathematical, the techniques for this, but one way that you have probably seen this kind of data reduction done is with web searches. So Google, for example, keeps all kinds of data for pages, and it wants to eventually transform all of those attributes into one attribute, which is a ranking for a particular search. So there we're going from a lot of attributes, and we have an algorithm that projects that down into a single ranking. Principal component analysis is a technique that's often used to do this. We are not going to probe deep into that in this class because it's a statistical procedure that's a little bit beyond what we're focused on here. And in fact, all of these data reduction techniques are much more back-end processing that then feeds visualizations rather than visualization techniques themselves. However, if you're creating visualizations, you want to know how to do this because ultimately you're often going to be the one dealing with the data. So if you need to do dimensionality reduction, there are statistical processes that you will hopefully learn in other places that can allow you to do that. And of course, there are plenty of tools that will automatically do feature selection or feature extraction for you, that when you learn those tools, you hopefully will have the skills to then apply the results to a visualization. So just to sum up, one of the problems that we have when we're working with big data is that there's so much of it and it's very complex, too big and too complex for people to understand in any form, especially in a visualization. And so you need to have some way to reduce the amount of data you're working with. There's a lot of techniques for doing that. Some of them, in fact, most of the ones we talked about today, involve cutting down on the number of items that you're visualizing. So you're going to throw out a lot of your data and hopefully still be able to get the same insights from the smaller data set that remains. You also can uncomplicate your data by reducing some of the attributes or features that you have about each item. There's a lot of extremely complex techniques that are designed to help reduce your data and to do it in a way that will allow you to still gain insight. We've taken an overview today. And if this is something that becomes part of the data you ultimately end up working with as a data scientist, you'll be able to focus in on more of those techniques and the specific mathematics and statistics of them in order to select the ones that are right for your application.